So my name's, if you weren't here last night, my name's Austin Schuh. I'm a software mentor for Team 971. So my goal today, and this is going to be a two-part class. Last year we did it in one 2-hour section, but this year we're going to have to do it in two 1-hour sections. So I would highly recommend you show up in the second version later tonight. We're just going to start right where we left off today. So we're going to talk about what's called test-driven development. So the idea here is basically that you start by writing a test case. So you have a behavior you want your robot to achieve. So say you want it to move an arm to a position and then stop. So the goal is to write some software to verify that our robot does that. And then after you have a test that makes sure it's going to work, we're going to go implement the code to implement that behavior. Does that make sense to people, the basic idea? So with robot, or with pure software where you're like testing an add addition function or a min and a max function, this is a lot easier to do because you can say put in a 1 and a 2 and get out a 3. You know, get out your answer and check it. With robots, it's a lot harder because we have physics involved. So the first thing we need to do, and this is what we started in on last night, is we're going to need to write a quick simulation of our robot. And then once we have a simulation, we can design software to control our simulation, and then write tests with that. And then after we have all those pieces, we can try it on a real robot and see how good we did. And if we did everything right, it should just work. So I'll start. I put together a skeleton just so that you don't have to watch me type up the skeleton. So the idea here is we have an elevator control loop. It's our interface for our control loop. So we have an update function, which is going to take the current encoder value. We have a Hall effect on this robot, a Hall effect sensor here. So it tells us when the elevator is at a certain position. We're going to call this position 0. You know, we need to define a coordinate system. So 0 is when the elevator is at the Hall effect sensor. And then it's going to take an enabled bit, so something from the field saying the robot's on or not. And then it's going to return a voltage, saying this is the voltage to command the motor. So it's a pretty straightforward interface, which we can actually implement a quick simulation for. So this is the skeleton for our test case. So I took the liberty of figuring out all the physics constants. So we have, it has a mini sim on it. So I grabbed the stall torque for mini sim, stall current, free speed, free current, estimated a mass for their elevator. We pull out, just like we did last night, here's our voltage constant, here's our torque constant, here's our gear ratio, computed a pulley radius. And then if we plug that into our, and since I didn't erase everything, we plug that into our equation from last night up here, we can compute an acceleration. So I typed that all up. So now the first thing we want to start with is we need to start implementing our simulation. So we have a quick start here called simulate time. So we're supposed to simulate a block of time. So can someone give me a suggestion for how we should start doing this?
No.
No. Yep.
You just have the equation you had from yesterday. And just,
Okay. Start giving me maybe not necessarily code that will compile, but things to start writing up. My goal is to make this interactive, so I want you guys to help me write this.
You need to make a reading. You need to do the encoder reading, and from that calculate your velocity for the elevator. Is this for the elevator? Yeah.
Yep, this is the
So
elevator.
you need to calculate your velocity. Yeah.
So let me give you a little bit more of a big picture. So let's start by, we're going to loop through 1 millisecond blocks out of our 10, and we're going to do Euler integration.
Okay.
So we're going to take the current acceleration, multiply by dt, and assume that gives us the velocity, and then take our velocity, multiply that by dt, and that gives us the change in position. So we're going to add to our position the current velocity times the amount of time that we're going to travel with this little time step. Then we'll do the same for the velocity. Take our current time step times the acceleration. You might want to modify this. Well, there's two ways to do this. I'll throw you both options, and then we can try and make a decision on what to do. So with simulate time here, we could provide it a voltage and then try and simulate a time step, or we could also try and run the control loop in there. Does anyone have an opinion which way to do it? I can pick one, otherwise.
Control loop.
Sorry,
With the control loop?
with the control loop in it?
Yeah.
So if we do that, we're going to have to simulate DT with 1 voltage and then change the voltage. And then do it again. So I'm kind of thinking it'd be simpler if we did it the other way. So we just provide the voltage. Okay. So then we want to create our control loop. Hey guys.
Sorry, guys.
No worries. So then we want to create our control loop, or our elevator loop. Where is it? So let's start with, we'll just simulate one quick time step. So we can do loop.update, and that will take the current encoder. And then whether or not the limit's triggered. And then whether or not it's enabled. And that's up to us, so we'll just say it's enabled. Okay, and then from there we could simulate time for so this will give us one step for KDT. So then if we wanted to simulate, say, a whole second or 100 cycles or something, how can we do that? You guys are really quiet.
Simulate time with 1 second as the input for time.
Is that what we actually want, though? What assumption are you making there? You're assuming that we don't want to change the voltage for a second.
Oh, yeah, so you're going to pass in a function there, but.
But we can make it simpler by we just compute the latest update from our control loop, simulate one control loop cycle worth of time, and then do it again. So we want to just call this whole thing for 1 second. So we can cheat and do it the simple way. We may want to refactor this later and be a little cleaner so we can pass in a time, but it's a good place to start. So let's walk through a little more what's going on here. So encoder, we've got written some functions up here. So we've got our encoder value is computed as the absolute position plus some offset. So this is, if you don't start the encoder where it's perfectly at 0, you start it off somewhere. You're going to get a different value for the encoder than your actual position. And then we need a simulation of our Hall effect sensor. So a pretty reasonable well, it's a little simplistic, but we could actually make it more complicated if we wanted. Is the Hall effect is going to trigger when the elevator is within a certain range of positions. So we can actually make this a little better. So this just assumes that if it's below a position, it triggers. So let's actually make it a little bit cleverer. So how would we make this our virtual Hall effect sensor trigger only when in a range of positions?
Value is less than a certain value?
And
Greater than the.
speak up.
And greater than.
Yeah.
And greater than another one, right?
Yeah.
Slightly lower. Yeah. It's not hard. Position. I'm trying to figure out how to start. So we should probably. Oh, I should be trying to eraser. I need to grab an eraser off the right now. way I like to structure the software for something like this is we're going to have a piece of the code whose job is to figure out where to go, and then a piece of the code whose job it is to go there. So you'll have, say, some goal coming in. This will go into our zeroing box. And this will go to a PID loop. Out to our hardware. So this box here lets us, so the driver will say, hey, I want to go to up here. And then this box says, okay, I'm zeroed, I'm going to give that to you. Or I'm not zeroed, let me first home. And then I'll give you your goal. And then it has, can command a goal to the PID loop. So the PID loop can then, we can move down in a slow, controlled manner to 0. And then once we found it, we could say implement motion profiling or something, or we could just jump to the goal. So we should start writing out some of those pieces. So if we want to track our status for zeroing, what's a way to do that? This function iterates, right? So we can't have any blocking calls in it. We can use a state machine. So we have a couple different modes our system can be in. It could be an unzeroed mode. It could be in kind of a zeroing mode. So we're going to start, we need to reset everything. And then we're going to slowly want to travel down. And then once we're zeroed, then we can just let the system perform, right? Does that make sense? Okay, so how can we implement that here?
Question, when you
Yeah.
say zeroing, you mean, so the zeroing box is going to bring the elevator down to the
Yep.
base? To that position?
This is how all 971 robots work.
Oh, okay.
You just don't see this part because we move it around. You'll see me wave all the robot pieces around before the match or one of our drivers. That's me zeroing it.
So every time you move into a position, you go down and then back up?
No, this is a good question. This is the crux of the problem. So what we do is we only need to do this once.
Cool.
Because, once per startup. So when you turn the robot on, right?
Okay.
So we start out, the elevator's right here, we turned on. What's the encoder gonna read?
Yeah, zero.
Yeah. But is this 0?
No.
Okay, so what we need to do is figure out what is the difference between where what is the position that we started at? Or the other way I like to say it is what is the offset between what the encoder reads and our absolute coordinates?
The block diagram is only for the first thing that you do ever, right? Since the zero.
No, actually, because the zeroing code could preempt your normal operation, or it could just say, okay, we are zeroed, let me pass the goal through.
Okay.
Yeah, this doesn't have to do anything
Yeah, I
crazy.
see. Yeah.
And you can layer some of these blocks if you want. So the first thing we're going to do is we're going to start moving, looking for our goal. In this case, we're going to make it simple. We're going to say our zeroing procedure is just going to slowly move down. 971's robot this year had a bunch of different procedures depending on where you started it, and none of which you ever saw in a match. So you can have more and more complicated zeroing procedures, but we can get away with a really simple one when we go down. Now, once we know this offset, do we ever need to do this again? Not until a reboot, right? So we just need to do this once, and then we're zeroed, and then we can go, work with the system from there.
How do you decide whether or not to have an explicit startup mode that does that versus having this in your controller?
This is our control loop.
Is the controller?
Yeah, we're going to implement the control loop in
Yeah,
here.
so my question is, how do you decide to put that zeroing procedure in the control loop versus
Oh.
a startup?
Now I get your question. Because you can't zero, at least on our robots, if it's an active zero, you can't zero till you're enabled. And what you also want to prevent is you want to design your software so your user can't mess it up. So if the driver doesn't hit the magic set of 3 buttons to make the robot work, they don't always remember that. It's the heat of the moment. They're not going to remember to press these 3 buttons before they run the match. So what we want to do is design software that's robust to these things and doesn't let the driver screw it up. So by putting it in here, he can ask for, the driver can ask for whatever he wants from the joysticks, and we will not let him do anything bad. So we're going to add some other checks in here too, like we're not going to let the driver request the elevator up here. We're not going to let it request it through the floor. A couple little checks like that, so we're going to prevent him from doing that stuff so we don't break the robot, and that makes the software more robust. So it's a great question.
Thank you.
And just to clarify,
Yeah.
so all your control loops are running from the beginning. All that driver input does is change states or inputs.
It changes, let me show you my interface. Oh, I closed it. This didn't wrap wonderfully, but, so here, update is our function that we need to call periodically to get the control loop to execute. And then there is a set goal function. So this is a rather simplistic goal. You could think of other goals we would want to give our system to have it do, like maybe we would want to tell it start auto stacking, or we could grow this to a much more complicated procedure. But for now, we're going to say we just want to take it to a position. So we're going to pass in a goal, and then we're going to let it do its work.
One other question.
Yeah.
So you said you're determining the offset. Why do you care where it started from?
Because say we're gonna try and stack boxes with this, right? We want to go down to a certain position so the box comes in, and then up to another position to make clearance.
Right, but when you're trying to zero it, why do you care where you started? You say you're trying to determine the offset?
Yes,
But-
we care because the encoder is going to read out 0 up here, and we want to know how to convert encoder units to real units. So one way the way to do that is you move till you find 0, and then you look at what the encoder read at that point, which will be the distance from where you started, and then you subtract out all the time, and then you're good. So we need to compute that offset so that we can zero.
Or ideally, you subtract that once and then put that in a value and then just use that value so you don't have
Or you put it in the value and then it automatically gets subtracted.
Yeah.
But yes, it's just designing your software to be robust in that way so that people can't accidentally get an unadjusted value. So, how do we want to? Anyone have any ideas for how to keep track of what part of this zeroing we're in?
You can do like a number variable, and then you first start at 0.
Yep. So we'll use C++ slightly more than that. We'll use an enum,
Okay.
which is just giving a name to a number.
Okay.
But yes, that's exactly what we need to do. So actually, we can draw out the state diagram for what's going to happen. So we're going to start out. Let me make some more space. So we have our, I'm going to propose actually, how about you guys propose some states? What's the first state we want to start in?
0,
Okay, which means what?
which means you're going to bring it down if it's not 0.
So this is a lowering state?
Yeah.
Okay. Okay, so we have a lowering state.
State where we are zeroing or just passing through the goal
Yep.
values.
Let's call this running.
Running.
Okay.
In your state before we lower?
Yeah, I want to have a disabled state. I like having this explicit so that when we can accurately represent what happens when it gets enabled. We have a disabled. Okay, so when do we transition from disabled to lowering?
When we enable?
Okay.
When we've enabled but just started up.
Input from the control system.
So we're going to start initial. So we're here, right? So when are we allowed? When do we go to lowering? When we're enabled, right? Okay. So now we're in lowering. Can we ever get back to disabled?
Yeah, you disable the way through.
Okay. Okay, we're in lowering. Can we get to running?
When you hit the call back.
Okay, so this is, I'm going to say write hall, but we'll have to figure out what that means in software. And then when we're in running, can we get to lowering or disabled?
Just disabled by disabling.
Okay, I'm going to draw that, and then we're going to see if that's a good idea. Okay, so this, if you're saying if disabled, and then if we enable, we go here again, right?
Yeah.
Is that what we actually want to do?
You don't need to, but
So this means that after autonomous, we go re-zero.
Oh, yeah, because, okay, yeah, that's normal.
So is there any harm in just leaving us in running?
Have another state which is like in-match disabled, but otherwise no. I guess you
So
just
let's
leave it.
try just with a running state, and if that does everything we need, then we'll leave it. Otherwise, we can add another state. I don't think we're going to need another state,
Okay.
but we'll see. Okay.
So do we need to have a limit in there such that if it travels X distance, we know that it started below the Hall effect sensor, and we don't want it to overrun the bottom?
I like to solve that mechanically, but you put the limit at the bottom rather than in the middle.
Okay.
But we can make this more complicated, but I think we should just ignore that and require the user to start it above.
Okay.
And then I would say in a competition robot, I'd recommend putting maybe a second one down at the bottom, so you know if you went too low and didn't find it. Or you could have a timeout if you wanted, where you've gone X and you didn't see it, that means something. There's a bunch of ways we need to change our state, right? Okay, if we're in running, so is that all the arrows? 1, 2, 3. Okay. So if we're in running, do we need to do anything?
Wait, I have a question. For
Yeah.
lowering, don't we have to start lowering it if we're not?
Very good. Okay, so how do you propose we do that?
Isn't this the control loop so you can just directly set like the voltage?
So,
Like you're inside the control loop, right? So you
Yep.
can like return the voltage.
but let's be more controlled than that.
Okay.
So I would propose that we tell our control loop to move down at a slow velocity. So this is where the disabled state comes in. So what we want to do is when we're disabled, we want to reset it to tell it to go where you started. And then every cycle, we want to move it down a little bit, move our goal down. And then when we feed that to our control loop, then it will slowly execute this path we've given it. So it'll start at the top and then slowly move down in a very controlled manner until we get to the limit sensor, and then it will jump to wherever we asked it. So, someone have a proposed way to do that?
Oh, I was gonna say carefully, but
You're sounding like me.
So that's gonna start in the, if you're not running.
Yep. So what do we do here?
Make value they need to return.
Sorry, speak up.
Make value they need to return.
Well, we need to set the goal for the control loop, right? This is our we have a goal coming in. This goes into our state machine. So we have our goal, it comes into the state machine, and then it produces a real goal, which it tells the control loop to go to, and then we send that out. That gives a voltage, which we then send to the hardware. So what we want to do is figure out how to generate a goal to do this. Conveniently, we have a goal. Actually, we'll start with this, and then there may be some more complications for it. So we want to tell it to start where we currently are. So how do we do that?
That's your encode.
Okay, good. Okay, and then if we're lowering, if we're disabled, we go back. We don't really need to update our goal. If the limit's triggered, then we're zeroed. So we don't really need to update our goal. We'll let the next case handle it. Otherwise, we want to move down slowly. How do we do that?
What?
give the
Yeah,
motor
no.
input at like a certain, like,
Hmm?
give the motor like a certain
Uh,
voltage.
But our output, we want to let the control loop do that. We want to generate a goal here.
Okay.
So how do we generate a goal that moves down slowly?
Whether or not it sees that value. It's like CC input or the Hall effect.
Sure, so that's deciding our edge transitions.
Yeah.
But if we don't see it yet, we want to tell it to go down a little bit.
So that's gonna be a if.
Yeah, if you don't see, like, if it doesn't see the Hall effect, keep going.
Okay. And how do we keep going? Goal minus equals steering velocity times dt. Does that make sense? Okay. So now we have something that's going to move through the states, and we need to implement it. So we want to implement a little PID loop here. So the basic idea is some proportional constant times our error. So now we need to compute a derivative. We should probably save an error and a last error.
Question.
Yes.
If this is velocity PID, why are we using the,
Doing position PID.
oh, for lowering?
Well, in the end, we want to take the elevator to a position, right?
Yeah, but while you're lowering, and the only knowledge that you have is you're going down at constant velocity, right?
Sure, but if we want to implement it that way, then we need to design a lowering control loop and an operating control loop.
Okay.
So if we can just use our operating control loop to do our lowering, then we can save ourselves a lot of design work. So you can just generate a slowly moving
Yeah.
system by just telling it to go down a little bit each time.
Yeah.
And that works pretty well. Our encoder value you're going to read when we start.
Our clear value is going to be still 0 in the real world, but here it's going to be 1.1, right?
Right, so what do we want to feed our simulation to be more accurate?
Um,
What do we want the encoder to read when we start this thing?
I mean, you could either do it
Reset the encoder at the start.
Okay, so how are we going to do this in our little simulation here? You can see the encoder function here. So if our position starts out at 0.1 and we have an offset, we want to add something to get it to, so the encoder will read 0. So we can set our offset to minus 0.1, right? And now our encoder will read 0, but will be at 0.1. So we'll start above it, yet read that we're at 0. So this will test to see if our 0 encode's working.
Why was the Hall effect on the chart plotting at 1?
Because we started at 0. And the definition of the Hall effect is right here.
Oh, okay, that's the Boolean. I thought it was the position of the Hall effect.
No,
Okay.
that's the Boolean.
Yeah, that's the value.
Okay. So let's try it. Oh, we're in state 1. So we're in our lowering state.
And Hall effect never actually triggers.
Yeah, Hall effect, yeah, never triggers. And the position, I think that's slowly going down.
I think we need a larger peak, maybe. Oh wait, this is really small time scale though.
It's coming down.
Yeah.
We're supposed to move 0.05 meters per second. So yeah, it's probably not a stiff enough loop yet. So we should crank it up.
Crazy.
Okay, we are actually a little after our, I think, our allotted time. So let's resume this in the next session. Thank you guys for coming. So,
That's the thing, like I was working on app development all last year, right? So like I know Java a lot more, but then they want to use C++ plus for robot this year.
That is a good plan.
so C++, we use C++, well, as you can imagine. But it lets you get access to exactly what's going on and really control it at the cost of being significantly more complicated.
Yeah.
So that's the trade-off. Okay, so we had something initially kind of working where we had a control loop that was trying to zero itself.
We were on, I think, turning the KP. So
Yes.
thing we were about to do. Yeah, cool.
So we ran it. Oh, hold on. No, that was me testing that part. Oh, there it is. So we run it, and then we plot. Yeah, it was not aggressive enough.
Wait.
So actually-
What's our goal in this one? Were we trying to get to 1? Or are we
we're
trying to?
get 0.
Okay. So, okay, I got it.
So we'll turn up KP. Doing by orders of magnitude.
What's the const expr?
That tells the compiler that this needs to be something that can be statically evaluated at compile time, like a number.
What about the
So-
voltage? Because you're setting a constant voltage, isn't that changing?
Not
Oh,
after
is
we,
it right?
not after we learn. Sorry, I'm being a little cute on my C++. And C++ 11. Oh, 3. Okay, so let's try it with a higher KP. And then the other thing is, if we look at our zeroing velocity, it's 0.05 meters per second. And if we go look at our test, we're spinning for 1 second, starting at 0.1. So we should probably simulate for longer, right? Nope, that's not here. We're gonna give it 5 seconds. Okay.
Okay.
We got a state change. It's really good.
What is the, oh, that's voltage, okay.
A state change? Oh. Okay, I see it.
Okay.
That took 2.5 seconds to settle. That's not bad, I mean, well, that's not bad.
I need to label this because I can't remember what the second column was.
Oh, but we changed direction.
This is actually red is voltage, right?
Yeah, must be.
Because it overshoots and then it doesn't resettle. Oh, that's actually something.
We need to tune this.
Actually, isn't that part of the simulation? Is that we shouldn't be able to go, oh wait, I forgot the.
It's a physics simulation. It should be exactly, if we did our simulation right, it should match that hardware.
No, I meant, okay.
Did we incorporate like inefficiency in the gearbox?
It's close enough. In the end, you want to pick your battles so we can make our simulation more and more complicated and more accurate and take
you're
longer
just
and longer on it.
Yeah, yeah.
And so the trick is knowing what to do, you know, what is the right amount. So conveniently, since I've worked on this robot before, I have enough constants for it that we're good enough. We can move on to that part. But yes, we could do fitting. There we go, voltage. Okay, so let's go look at. Let's look at our response. Still looks a little weak. So we can make KP stronger.
Wait, so which one, so is the
Do you
green
want-
one the R1? No, no,
Green's
no.
position.
Oh, okay.
Do we want to turn up the time scale so we can actually see how long it takes to actually settle on positions? Since right now it.
Well, at some
settles.
level, if it takes longer than a second, I think we're doing it wrong.
Okay.
Is that a valid statement? I mean, if it takes longer than a second to settle down to pick up a box, then
Yeah.
we need to be faster. So we can, but I don't think we should.
Do you do the thing where you turn up KP until you get an oscillatory response and then?
If you really want to know what I do, I don't use PID loops.
I thought you used someone, but
I
you
use
don't use
state
any
space
anymore?
controllers.
No, they
You
do,
just use-
yeah,
It's
state
pushed
space.
the limits in other ways.
Okay.
So let's do the little bit of tuning, and then I want to, we should sure our test is working, okay? Because right now our test is just a simulation, but it's not actually validating anything. If we were to return 0, the test would still pass, which is not a good thing in a test. It should fail if we don't have a control loop. So let's see what happens with a KP of 100. That looks better, honestly.
We stopped,
The voltage converges.
we stopped decrementing the target when we hit town hall.
Yeah.
Yeah,
So
I
is
think so.
voltage captive? Like, no, it can't, it's not captive.
Okay. So, let's write tests for that, okay? So we'll go back to our test fixture here. So right now we're not verifying anything. So what are some things that we can check to see if our control loop is succeeding?
Position.
You can see if it goes, the position goes below 0.
Yeah. Well, so
Position is.
let's expand that a little bit. So if we went down and crashed this into the floor, that'd be a bad thing, right?
Yeah,
If we went above the top, that'd be a bad thing.
yeah. So you just basically just have a range.
So let's add a check and simulate time, so that if it's ever outside the physical limits of the hardware, that's
It
a
just
failure.
stops, yeah.
Okay. Well, it fails the test.
Yeah.
So we can do,
Because that would, in real life, be.
Yeah.
so this is just more syntax. So we're going to expect that the position is greater than, I think I wrote down the limit somewhere here. It's in the other class. Min height.
Then you do right?
Yep.
Is there any reason you're not using assert in this instance? Because I mean, there's no real, if it passes
Well,
that.
Generally, you want to use this. So there's two ways. When something like this fails, there's two things you can do. One is you can completely shut the program down, and the other is you can mark the test as failed and try and continue and see what happens. So expect says, okay, if this fails, mark it down as a test failure and then keep simulating. Assert would just kill it. So here, it's not like there's going to be a null pointer exception. We're just going to violate the hardware limits. So there's no cost in going on, and we can then see what it would have happened
Right.
and see how bad it would have been. So, and it's a simulation, right? We're not going to break anything,
Yeah.
so who really cares? So that's why expect is a better use here.
Expect, use that?
So
This is a G test. Google has a C++
Yeah.
test framework,
Yeah.
which works great.
I need to learn that.
Yeah. Okay, that's a good part. So that'll tell us if we try and break it. So now how are we going to tell if it has succeeded in zeroing?
Just, if it's, after 1 second, it's at 0. So when time equals a second, then the position is 0.
Well, what we want to ask is, did the position become the goal after a second?
Okay.
After we finish zeroing, did it become the goal? And also another thing we can check is, did our state become right?
Yeah.
So we have a little state machine in here.
Yeah. Does state change?
Do we care about its set line?
Yeah.
Okay.
Well, why not, right?
Yeah, okay.
So
So you have one at
Because
a time.
if our control loop does not converge within, say, 5 seconds, that's also a bad thing. So we can just test that by saying, did the position go to where we expected it to?
Okay.
Within some epsilon. But, so here's our state. So let's also check to see if we got the state running. So, okay. Okay. And then we want to say expect. Can't remember the syntax. We'll just do. Huh. It's been a little while.
Yeah. And then the range,
Oh, that's a
the
good
range
one.
is the third term.
Oh, is it? Val 1, Val 2, absolute error. Cool.
Is there any for Bruce Gunner, Jared?
I mean, you can define more and more macros, but there's not one built in for that. Yeah, okay. Expect near.
Do you have a lot of hotkeys or something? Like you just go everywhere so quickly.
Oh, I have a bunch of virtual desktops set up. Alt ASDF between them. So I can very quickly get between them. Yeah.
And yeah,
So we want to make sure the position is near. Actually, that's a good question. Where did we tell it to go?
Position, we wanted to go to 0.
Actually, I thought.
Did we tell it to?
We told it just to go slightly below where it was, and then we kept telling it to do that until it hit 0.
Yes, but that is our zeroing procedure. That's not our absolute goal.
Not our.
So I will say we didn't tell it to go anywhere.
Oh. Okay.
So we should.
Cool.
So loop. Let's check the header. Can't remember what it's called. Set goal. We'll go a 1/10 of a meter down. So then we want to say expect near position. And then say we're within half an inch or half a centimeter. Seem reasonable?
Yeah.
hopefully, yeah.
Okay. Well, see what happens. Not bad, but that's right. I believe it should fail. Fast.
Wait, will that not check if it's steady state at the position, but only?
Yeah, I would just.
Well,
Oh,
so
yeah,
it's-
after 5.
we're waiting quite a while.
Yeah, okay. Yeah. Grab that outside the loop.
Ooh, pass. Right, I feel like this expecting near shouldn't have succeeded. Okay.
You're just too good, man.
When you're doing your simulations, do you ever incorporate simulated noise?
Yep.
Okay.
For this system, it's not worth it yet. But you can measure how good you need to be and go from there. Okay, so what can we print out to kind of help us figure out what went wrong?
You could you already returning the, wait, actually print out the voltage.
We did.
Okay.
So this right here, this voltage that we returned, it's over here, is that return value here, 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 here.
Okay.
So we're printing the voltage out.
Okay.
I know what's wrong. Let's see if you guys come up with it.
You can print out the goal. Oh, except that's
Which goal? That's a
The-
good point. Which one?
The negative 0.2 anus. Goes
Okay.
that one.
Well, that's going to be a constant.
Okay.
What is that? Can we look at the second?
But yeah,
first one?
So yeah, you're not gonna. That's not gonna, the one that changed.
Yes.
Yeah, the actual cycle function. Oh, so
It's just setting this.
goal equals goal. Where's goal code in the actual control loop goal _?
Yep. Well, but we could print this out, right? See what's happening?
Yeah.
Make sure it's getting set right.
And then maybe also print out error, just to see if it's, well, no, never mind.
Well, I mean, you could.
We could.
Why not?
More plots never heard.
Oh, it's just more typing.
That's all.
Yeah.
I get to watch.
No, we're going to start with this. So I think it'll be lighting. Okay, so now let's go into our simulation here. Okay. Got it. Oh, look at that.
What happened? Oh.
So our goal,
Oh,
yeah.
because it's getting overridden by the calibration.
Yep. Did you catch that? Catch what's wrong?
I think.
So our calibration routine is changing the goal.
Oh.
So we
Oh, I
set
see.
it, we set it to -1 before we start calibrating, and then once we start calibrating, it sets
It
it.
just changes it.
Goes, okay.
So there's a bunch of ways to fix this. Does someone have a suggestion?
Say if we're not in the lowering state, just like put the set goal in our calibration thing in a, if we're in the lowering state.
I guess can you, so we would only change the goal down here, or I don't get your proposal? Did you have one? Yeah, you started to speak.
I don't know what's happening enough.
Okay, so what part have I lost you at?
I think all the stuff you covered in the first one.
Okay. So it's, yeah, so this is a piece of code. We have a state machine here. We start out disabled. On enable, we go to a lowering state, and then we slowly move a goal down. And then when we've found the Hall effect, we go to a running state. So you can see that in the switch statement there.
What's the Hall effect?
Okay.
It's like
So
it's
here's a magnet
basically
here
just, yeah.
and a sensor here. So it's a Hall effect sensor.
So
which
basically
detects
just-
magnetic fields.
yeah.
So as the elevator comes down, it's a contactless sensor to tell you when you get to 0.
Oh, okay.
Can I ask a quick question about the Hall effect that you guys use?
Yeah, I designed it.
Because I know like a lot of the ones we buy have basically an arbitrary limit on the flux that they return high. Do you know of any ones that actually allow you to configure?
The data sheets are not very precise.
No, I mean like ones where they give an analog output
Yes,
so that.
you can buy those. The same chip family will have that.
Oh, so it's all the ones we see that are analog or like these tiny little things that aren't actually.
Oh, you can't buy a board for it. So me and some of the students on 971 designed the board sold by West Coast Products.
Oh, okay,
So
cool.
So that's only commercially available because we got tired of making our own.
Okay.
So the way I like to solve this one is we have the absolute goal, which we don't change, and we have a filtered goal, which is one that we can do whatever we like to, including motion profile if we wanted. And then that makes it so that we can kind of save it. So we can go here,
Yeah, why do you have two different programs? Like,
because I can flip between them faster.
oh, okay. That's why, okay.
Do you have all this stuff saved for the second session?
Yeah, I checked it in the Git beforehand, so I can revert it.
Oh, is this on a public kit or is it on a private?
It's actually in someone's code base.
The private one or the public one?
It's whatever the local version I have is.
Okay.
But I'll release all this one.
Yeah.
Cool.
So you guys can go back and look at it when you have time. So let's change all this to filter goal. And then in running, we can just use filtered goal. So we'll just pass it through, and that way we're not modifying the goal that we want to go to.
Okay.
Okay, and then we want to have our error be defined on filtered goal. Okay. Okay, so maybe that'll work. Let's try it.
Oh wait, we didn't actually accept the. We
Oh,
didn't
did
fix
we,
the test.
did our test still?
It's our test is still
Yeah.
trying to break.
Good. Well, it's successfully still broke.
Yay.
It's always a plus.
Yeah. And this is another actually really valuable lesson. It's worth making, before you implement a feature, make sure your test fails when it's not implemented.
Yeah.
Otherwise, you get this false sense of I fixed it and it works, and you actually have no clue. So one of the basic ideas in test-driven development is you write the test first to make sure it fails, and then you go implement the feature. Now, in real life, we tend not to be that diligent, and we kind of mix the two. But the end point is you want to make sure that if it doesn't work, your test fails, and when you then fix it, your test succeeds. And if you find a bug in your robot code, you go write a test that reproduces the bug, and then your test fails, and you fix it, and your test passes. And now you've both fixed your bug, and you're aware that you fixed it, and it'll never come back again because you have a test for it.
Passes still.
Yeah.
The bug will never come back again.
In theory, it may be a different bug. Okay, so let's try this. Okay, test pass. That's awesome. Boom. Okay,
That looks nice.
this is much better.
I like that a
Now,
lot.
let's look at our overshoot, undershoot, and see what I
Wait.
get. We're overshooting slightly.
It looked like the voltage was, what should I call it, going below 12.
Okay, it is.
Oh, yeah. Yeah,
So
that's
this is-
what we have to cap.
So this is another point that I'd like to bring up. Yes, we should cap it, because if we're asking for crazy values, that generally means something's wrong.
Well.
Another thing is, if we don't know where it's a way of checking to see if you're internally consistent. Did you handle all the cases? Did you think about saturation?
Okay.
So we should probably just cap it in the control loop. Another thing is, if we don't know where we are yet, because we're not zeroed, should we be allowing full 12 volts to our motor?
So in the
Very good. So we should add a feature. Actually, the first thing we should do is we should write a test to verify that it doesn't work right now. Then we should fix it.
Just to make sure I'm understanding, it's only going -12 right now in the target stage, like after we zero, right? Yeah, so, okay, so that's just a precaution to
Yeah, I'm partially exposing some of the standard practices we do in 971 as we go through this. I mean, we wouldn't use a PID loop here, we use a more complicated controller,
Yeah.
but all of the rest of the stuff is what we do. So, this is good practice.
Yeah.
So let's add a test for it. So how would we test this?
have the target velocity for.
You're thinking.
I am thinking, but now that everyone's eyes on me, my thinking is going away and I'm panicking.
So conceptually, what do we want to do?
Okay.
Don't worry about the syntax. I'll take care of the syntax.
So if it's drawing all power, why is it drawing all power? I don't know.
Okay. So the reason it's jumping is because our control loop is unbounded. But we'd like to add a test saying, okay, we
Oh, I
shouldn't
see.
be commanding this, right? So how do we write that? Where do we want to write that test?
Just make a
How
test
do we
that-
slot that in?
Says you can't go this far.
I can't go this far, or we just
You have
check
to stay
see
near.
if the voltage
You
is
can
right.
do like an expect near.
Right?
Yeah,
See if the voltage is
if
outside.
voltage
Yeah, you can
is
just-
out
oh.
of
So if
parameters.
Wait, couldn't you use
tell
like
me.
an expect near? for
So I'm
that?
going to do mine slightly more complicated. If loop state is not equal to elevator loop, if it's not equal to running, then we're going to verify we're below a smaller threshold. And then if it's running, we'll make sure it's inside 12. Okay. Let's try it. Oh, test failed. Okay. So let's go fix it. So here, since we don't have integral, there's no other complication, so we can just limit it to 12, plus or minus 12 here. Well, actually, no, we want to be more clever than that. So if we're zeroing, we want to limit it to one value. And if we're running, we want to limit to another.
So 6 and 12.
So.
Would that still screw with the, okay, never mind. Yeah, that's only,
Could you set that voltage limit in the different in the state machine?
No.
Oh, yeah.
No, I was just going to do that here.
Okay.
pretty complex.
I do it at zero in voltage. I do it at max voltage. Okay. So then you want to, if voltage is really good, we get constant. Okay. Test pass. Cool. So what we should also try doing is trying to zero too fast and make sure that works, right? So, conveniently, we have a zeroing velocity.